hope that it will not be very hard because definitely, sorry, these talks are really very, very interesting. The first speaker is Guinea. I mean, he doesn't need really any introduction. He is one of the best theoretical leaders of graphene, and it's been right there from the beginning. And he's going to talk about graphene and its unique properties apart from some gauge fields that he has found predictable out of his theories. So welcome.
Thank you. I really appreciate the opportunity of being here. I have profited a lot already from this morning session. And I also like to start by acknowledging the many collaborators I have had while working on graphene. I've learned a lot from all of them. I will discuss a bit about graphene with emphasis on graphene and magnetic fields. Magnetic fields which can be of two types. The real magnetic fields in which you all are interested in, and some other magnetic fields you can create in graphene and not in other materials. Before I want to mention that, of course, graphene is not the only carbon allotrope which has caused a lot of interest in the scientific community. There are many of them nowadays. We can consider almost all of them as graphene in its guise, in a cylindrical shape or in a spherical shape. Let me also mention that graphene was kind of predicted way back, and I always like to show this slide to everybody because all the things you find in graphene are kind of special and unique, but if you are like Julius Verne and so on, you could imagine that such material existed. This is the famous way of fabricating graphene, which led to the Nobel Prize 2 years ago. And you probably, all of you are familiar with this technique, and at the end of the day what you have is these very tiny bluish flakes which eventually you can identify as monolayer graphene. And this is the way it started with these two papers where it was discussed that you can exfoliate graphite all the way to one single atomic layer, and not only that, but you could also use an electric field and induce carriers. Moreover, those carriers have a very high mobility. And after that, people started to do research extensively on graphene, and this is more or less definitive list of unique properties graphene has. Graphene combines many records in material science, like being very stretchable. You can expand it up to 15% at least in a reversible way. If you think of, for instance, Lindemann's criterion, when crystals break, typically they melt when the interatomic, the lattice spacing changes by about, or fluctuates by about 2 or 3%, and it's very special that you can stretch graphene like 3 times that much or more, and still it's stable, and you can go back to the original graphene by relaxing the stresses. But what put graphene on the map were its unique transport properties. They were realized very quickly, especially the high intrinsic mobility. Graphene is also helped by the fact that carbon is very light. So not only carriers in graphene have an excellent mobility at low temperatures, but then if you go to high temperatures, then graphene beats all other materials, basically because phonons are very energetic in graphene because of the lightness of the carbon atom, and because of that the high mobility electrons or holes have in graphene remains at room temperature, while copper or silver that's not the case. There is an open discussion of how unique graphene is. Probably it is indeed a unique material in the sense that it doesn't have all the complexities a material with many different elements in the unit cell, a very complex unit cell and so on has. It has a very simple lattice structure, a very simple but unique electronic structure in the sense that carriers are massless and so on. And because of that, despite the fact that it's two-dimensional and it's totally exposed to the environment and so on, it retains its properties. I mean, it's very stable in all respects. And it's easy to manipulate. You can manipulate a single layer of graphene, which probably nobody thought, a monoatomic layer of something, nobody thought it was probably feasible before graphene was isolated. But the papers, as I mentioned, people realized that graphene was a very interesting material because of its transport properties, and the papers were really put graphene on the map, which boosted the graphene research, were these two papers. Let me mention that the two previous papers, which eventually led to the Nobel Prize, were rejected by Nature, but Nature was quick to realize the mistake it made and quickly accepted these other two papers soon afterwards. These two papers showed that it was very easy to find the quantum Hall effect in graphene. Not only that, but the quantum Hall effect graphene showed was special. It didn't fit the usual degeneracies and so on you have in a two-dimensional electron gas, and it showed that carriers in graphene were massless. I mean, it was the only consistent explanation of the degeneracies and the level spacings and so on you found in the quantum Hall regime was by assuming that the carriers in graphene were massless, which can be easily justified theoretically. So that really showed that graphene was a very unique material and really started the big boom of graphene research we're still experiencing nowadays. A bit later, the same experimental groups which showed the existence of the quantum Hall effect in graphene, so I'm already talking about magnetic fields, showed that graphene was such a high mobility material and so special that you could also see the quantum Hall effect at room temperature, and that had not been seen before in any other material. Moreover, as graphene is purely two-dimensional, you can image directly what's going on in a magnetic field, and I think for the first time people reported the Landau levels of a two-dimensional metallic system directly seen with a scanning tunneling microscope. And then later, and that was a bit surprising because it took a long time, people managed to show that graphene also exhibited the fractional quantum Hall effect. Actually, those were lousy experiments in the sense that they were two probe experiments, not very controlled. People were looking forward towards the fractional quantum Hall effect in graphene, and these hints, because they were nothing but hints at that time, of the one-third fractional quantum Hall effect were quickly accepted by the community. And this, in order to finish about real magnetic fields, these are very recent experiments being carried on now in Manchester and Grenoble at much higher magnetic fields, as you see here. And graphene is so special that not only has the famous Dirac points, which define the massless carriers of graphene, it can have secondary Dirac points. If you put very clean graphene, high mobility graphene on boron nitride, which is the best substrate people have discovered for graphene, for experiments on graphene, then the mismatch between the two hexagonal lattices creates an extra hexagonal superlattice which can have its own extra Dirac points. And then if you look to the Landau levels, you have the Landau levels, like here for instance. These are these lines in the resistivity or the conductivity versus magnetic field. These lines correspond to the plateaus in the quantum Hall effect, but you have extra lines associated at finite carrier concentrations, which carrier concentration is determined by the gate voltage, and they are related to the existence of extra Dirac points in this kind of moiré system. And then you can go to, if you go to very high magnetic field, you're close to realizing the so-called Hofstadter butterfly, which is to total breakdown of Landau levels when the flux per unit cell is comparable to one quantum of flux, and that you can achieve in graphene on boron nitride, because then you have a super lattice. You don't need such a high magnetic field. You can get away with 40 Teslas or something like that, and you're already close to this special regime. These are unpublished results, but they will be published shortly. You can get close for the first time to this regime, very heavily studied theoretically, of the Hofstadter butterfly. But now, okay, this is a bit of a general introduction to graphene and some things graphene shows in magnetic fields. Probably there are many more. I mean, the fractional quantum Hall effect already has, in graphene, has proven to be special in the sense that the gaps, the activation gaps, are much higher than in other two-dimensional systems. There's no reason why, because the fractional quantum Hall effect is solely determined by the electron-electron interaction, and that doesn't change. That the interaction is the same irrespective of whether you have Dirac fermions or massless fermions or regular fermions. So the fractional quantum Hall effect in graphene is already special, and who knows what will come if one can reach, put graphene under higher magnetic fields and go beyond the fractional quantum Hall regime. Now I'm going to speak about another way of changing the electronic properties of graphene, which mimics in many ways what a real magnetic field does. And that is strains. And strains are associated to lattice correlations, lattice deformations, and ripples. Graphene is a two-dimensional system, but it has been always correlated. There's this famous paper which started a whole subfield about ripples in graphene. They were studying suspended graphene, and it was realized that it was by no means flat. It had been widely discussed because there is this famous Melvin-Wagner theorem, according to which two-dimensional crystals shouldn't exist. And people claim, well, maybe this is the explanation of these ripples. They're still unexplained, and moreover, ripples in graphene have been found basically in all possible graphene samples one can imagine. They can be graphene on metals, or graphene on silicon oxide, or graphene on silicon created out of silicon carbide. But graphene is never a really flat system. It's always corrugated, the lattice is always distorted, and as I mentioned before, and it's discussed in these experiments, graphene is an incredibly stiff material, much stiffer than diamond, which had the record before graphene was studied. And moreover, the breaking strength, how much you have how large a stress you have to apply to graphene before it breaks is very, very large. So that's what I meant, and that was proven here, that you can stretch graphene all the way to 15% or more, and graphene remains graphene. It survives pretty well. You relax the strain and you go back to your original system with the same electron mobility and so on. As I said, highly strained graphene clearly exists, but it has to be a metastable system because it has a lot of elastic energy built into it. But why it doesn't break, why cracks are not created is unclear. Probably related to this incredible stability graphene has, and maybe it's because the formation energy of defects like these locations and so on is very high, but definitely it's a fact. And nowadays you can manipulate strains. People have started to create strains on demand, so you can generate some strains by playing with the thermal expansion coefficient of graphene and that of the substrate and things like that, or you can create graphene balloons at nanometer scale or micron scale. So nowadays there is a starting kind of a topic which people call strain engineering, which has started in graphene, and the idea is to create whatever lattice deformation you want on graphene one way or another. And strains or lattice deformations in graphene give rise to interesting effects. And we started this thinking about that way before graphene, in the Jurassic times, because the fullerenes existed, and if you think of a fullerene, carbon-60 for instance, it's like a graphene lattice with defects. The defects are pentagons. You need pentagons in order to have to close a sphere. And if a pentagon technically is what is called a disclination. You can think of a pentagon as a defect you create by cutting out a part of a graphene lattice like that and identifying the edges. Now, if you do that, graphene has an internal degree of freedom, an internal quantum number called pseudospin, and that's related to the fact that the honeycomb lattice, which defines graphene, has can be divided into two inequivalent sublattices, and then if you create a wave packet, you have to specify the amplitude of that wave packet living in one sublattice and in the other. So, by definition, any electronic state contains this internal degree of freedom, which tells you how likely is it to find the electron in one in one sublattice or the other. When you glue the two edges which define a pentagon, you have to exchange the sublattices. You're gluing the red sublattice and the blue and the green sublattice, and that means that an electron which moves around the pentagon, it will fill most of the time a local environment, which is basically that of flat graphene, but when it goes around the pentagon, this internal degree of freedom has to change. It has to go from +1 to -1, for instance. And that kind of thing, when an internal degree of freedom of a quantum object changes along its path, when it moves along a given path, that is something which you can describe by a gauge field. The usual magnetic field, what it does, it changes the degree of freedom you call the phase of the wave function. So when an electron moves in an electromagnetic field, if the quantum nature of the electron shows up in changes in the phase due to the particular path or how many flux quanta and so on that particular path encloses and so on. And the same thing happens with the pseudospin. So you can replace the pentagon by an effective magnetic vortex, and out of it you get a description for the electronic structure of fullerene in terms of flat graphene, a flat honeycomb lattice, plus a monopole sitting at the center, and you have a very nice and very simple analytic description of the electronic states of the fullerenes. And same thing applies to strains. If you, not exactly the same, but almost, if you stretch graphene, you are also changing the hopping integral. You're also changing how one electron moves from atom to atom. I didn't mention it's already, probably have heard it already a number of times, that in order to build up the electronic bands of graphene, you just need to take into account 1 pi orbital per carbon atom. And out of that very simple type binding description, you get all you need to know about the electronic bands of graphene. Okay, if graphene is stretched, the hopping elements between neighboring carbon atoms are changed. So, I mean, you have made the lattice anisotropic, and because of it, the Fermi velocity and other electronic parameters depend on the orientation, on the direction. If you put it into an effective model and simplify it all the way until you only have Dirac cones, massless electrons, you see that you have changed hoppings. The hoppings come in this way into the effective Hamiltonian, and at the end of the day what you have is an extra term which you have to add to the momentum operator. As I said, the technicalities are not very involved, and this is just a question of taking the right limits and so on. It's not that difficult to go from tight binding, which is this, to this. So at the end of the day what you have is that the strained part of graphene looks like graphene itself, except that there is an extra constant which tells you how much the lattice has been stretched. Now, something which you add to the momentum operator is a gauge field in quantum mechanics, and you can show that this is actually a gauge field, because if you do a kind of Gedanken experiment where you shoot electrons through an interface between unstrained and strained graphene, you calculate the trajectory of these electrons, it is bended at the interface. And that is what you also expect from a real magnetic field, which is located right at the interface. So this is a pictorial way of showing that strains can play the role of effective gauge fields. If the gauge field is constant, not very much changes here or there, because here you have a gauge field which is constant and zero, and here you have a gauge field which is just constant and finite. Nevertheless, you have Diracons on both sides, but something special happens when the gauge field is changing, which is at the interface. I mean, you can relate the strength of this effective gauge field to the change of hopping with bond length, which in turn is related to the electron-phonon coupling and so on. So actually, to some extent, this is like speaking in prose. These things were already known in the graphite literature, or in the literature related to graphite intercalation compounds. That in a way, some of the couplings to phonons play the role of gauge fields, and the only thing we have done so far is to generalize it to static strains. But then you can think which kind of gauge fields you can generate, and these are possible deformations you can create in a graphene quantum dot by applying the right forces at the boundary. I mean, this is a dislocation. These are really deformations which come out of forces at the boundaries. And these are the effective magnetic fields you can generate, and the color code is such that if blue is positive, red is negative. So typically you have deformations which generate effective magnetic fields which on the average are zero. There is a very simple deformation which is just a uniaxial deformation, a stretching of graphene, that you always have when you have a suspended graphene, which has been a hot topic in graphene research for a long time. If you have a gate, you have graphene, this is a capacitor, and then you create elastic strains in the suspended region. So here you have an interface between a region where graphene is under strain and another region where the strain is zero. So this is precisely a realization of the Gedanken experiment I mentioned to you before. And that means that no matter how clean your graphene is, the electron trajectories are always going to be deflected at these boundaries. And that's a general property of strains. And actually that's why we speculated using this scheme that that's probably why it was always so difficult to observe the quantum Hall effect, because they were looking for the quantum Hall effect in the cleanest graphene samples available, which were suspended samples. And these suspended samples have strains. And then if you look to a property which depends on the magnetic field, and you have something which looks like a magnetic field which interferes with this external magnetic field, you're obviously in trouble. By the way, this is a realization of a famous thing mentioned by the Royal Swedish Academy of Sciences, that you can make a graphene hammock which supports a cat. And the weight of the hammock is less than the weight of a whisker of the cat, and in addition it's transparent. Okay, and there is finally another distortion you can create, which is trigonal, and it turns out that this trigonal distortion matches the trigonal symmetry of the graphene lattice, and this distortion allows you to have a constant magnetic field. And these are different ways we thought at the time of creating such a distortion, by having a graphene quantum dot and applying stresses at the boundary. And these are estimates. So with a 10% strain difference between the center and the sides, you could get all the way to 40 effective Teslas in such a setup. And at the end of the day, in addition, you have something like a topological insulator, because or a quantum Hall system, because you have actually Landau levels in the middle. You have edge currents at the edges. They are valley currents because they are associated to the valley polarization graphene has, because it has two inequivalent valleys. So it was a neat way of creating gaps inside. We thought it was a neat way of creating gaps in graphene, and fabricating some kind of artificial topological insulator out of, and then we estimate the limitations of this situation and so on and so on in the paper I mentioned before. And in order to show you that all this is not science fiction, it turns out that you can measure these effects at least in highly strained graphene samples, which turn out to be graphene nanobubbles, which you have when you grow graphene on a metal, the so-called CVD graphene. It's also not flat. From time to time you have bubbles. And Micron's group, they work on the STM measurements on graphene and other materials. They realized that the spectra they found on top of the bubbles was totally different from the spectra they had elsewhere. The black line is the spectra in the bubbles. The spectra they found when they looked at the bubbles, they imaged the bubbles, and it had resonances which were absent elsewhere. Then my colleague Antonio Castroneto was on sabbatical in Berkeley at the time and told them, oh, maybe those are Landau levels. And they took the suggestion seriously, and they measured the position of these resonances in great detail, and then they fit the distance between resonances according to the behavior you expected if they were Landau levels induced by a real magnetic field, and the fit was pretty good. And out of it, they got this effective magnetic field acting on the electrons which were moving inside the bubbles, and this effective magnetic field, the fit was above 300 Tesla, which was quite remarkable. And actually you can justify theoretically this analysis pretty well just by assuming that the bubbles are under strain. The only free parameter you use is the strain, and you just need a strain of 10% to fit this data and the existence of an effective field of 300 Tesla. So this everything was pretty consistent with the analysis I presented to you before. After that, people have designed strain graphene on purpose. This is done by Haran's group in Stanford. This is a completely different setup. Here what they created was artificial graphene by modulating an image, a surface state in copper by putting molecules on top of the copper surface on particular positions. The main, the great merit of this work is that they had a very clean copper surface, and they could put carbon oxide molecules directly where they wanted, so they could mimic a graphene flake without and with strains, and then they measured the density of states, and suspected they also saw a sharp resonance where it should be, which corresponds to a Landau level, at the Dirac point. So this is another way of showing that if you apply strains to graphene, you create the same effect as in a magnetic field. These are more recent experiments, and again, they are all STM, they directly image the density of states of strain graphene. And definitely now, I think there is a consensus that indeed strains induce effects on the electrons in graphene, which are very similar to what you expect from a real magnetic field. Now, what can happen if you have a real magnetic, I'm going just briefly to go through possible things which can be done. If you have a real magnetic field in addition to this fictitious magnetic field induced by strains, you can create new devices. You can, first of all, as I said, you can have problems if you are trying to measure delicate properties like the fractional quantum Hall effect in a magnetic field and you have strains. But on the other hand, you can play with the real and the fictitious magnetic field, and now you can create different things, because you can, the fictitious magnetic field has both signs depending on which value of graphene you're looking at. You have a strain creates a positive or a negative magnetic field, so you can, by applying a real magnetic field, you can cancel one of the total field acting in one value and you enhance the field in the other. You can also play with the strains you have in a graphene fold, and then you have like a cheap interferometer. If you have a real magnetic field, you will have edge states. The strains associated with the fold will create extra extra magnetic fields which generate new effects, and we can use this situation as an interferometer. Okay, this I don't have time to discuss the role of interactions in all the electron-electron interactions. So let me just, that's a new thing which is coming up. Let me just finish. This is a general slide I have for graphene. I have discussed here, because that's the main emphasis of this meeting, graphene in a real magnetic field and graphene in a fictitious magnetic field, but graphene is a very rich material. Here is a list of a few of the many open problems which I think are probably very interesting and will be hot topics in the future. Thank you for your attention.
Thank you very much, Paco.
How does a pseudomagnetic field break time reversals?
No, it doesn't. That's a good question. That's why I said graphene has two values related by time reversal symmetry. K and K prime. And then the effective magnetic field is positive for one value and negative for the other. That's why it doesn't break time reversal symmetry. And I also forgot to mention, this is an orbital magnetic field, a fictitious orbital magnetic field. It doesn't couple directly to the spin, and the spin, I mean, only through the spin-orbit coupling, which is weak in graphene.
Does it mean that these gauge fields do not have any relevance to make the graphene interesting for spintronics?
Well, that's another good question. In graphene spintronics, there are many unresolved questions, because the idea is that the spin-orbit coupling graphene is very weak, so that makes the graphene very convenient for spin qubits and so on. Experimentally, that's not so clear, and the spin diffusion length and so on is relatively short. Why short is unclear. A possibility is that if you have sufficient strength through the spin orbit, they enhance the spin-orbit coupling, and they lower they lower your spin diffusion length and things like that. So it may play a role, maybe a negative role.
Yeah.
Who knows?
How far does the analogy to magnetic field carry actually? Could you have quantum Hall effect just based on this?
Yeah, only it will not break time reversal symmetry. It's slightly different from the usual quantum Hall effect, but yes, it's an orbital magnetic field. That's a nice feature of graphene. I mean, below 0.5 electron volts, graphene is, carriers in graphene are very well described by the Dirac equation. There's no question about that. If you trust the Dirac equation, this is all right. I mean, a sufficiently long wavelength strain is equivalent to an effective gauge field. So in that respect, the only thing is that in order to get a constant magnetic field, you need a strain which is modulated, and the modulation of the strain is the non-trivial part.
That experiment with the bubbles with STM, that the spectra was really very different on the bubbles. They were on-purpose bubbles or just natural bubbles?
They were natural bubbles. The idea is that something was trapped below graphene, and then it concentrated below. People have found bubbles of all sizes in graphene, even micron-sized bubbles. But those bubbles are very general. There is also a nice thing about those bubbles. They were triangular, and that has the right symmetry for creating a very large effective magnetic.
What does it mean, the question, can graphene be divided by 4?
Oh, because if you listen to talks of experts in topological insulators, some of them start by saying, well, a topological insulator is like graphene divided by 4. And that's correct, because graphene has Valley and spin degeneracy, and a topological insulator is the same thing. It's one Dirac cone with no degeneracy whatsoever, the surface of a topological insulator. So the question is, can you turn graphene into a topological insulator? My answer is that probably you can, if you work hard. And topological insulators have a lot of materials problems, so maybe it's worth a look again into graphene and see if you, by manipulating it in the right way, you can turn it into a topological insulator. But you have to break the spin and Valley degeneracy to do that.
No more questions? Okay, thanks the speaker again.